example. So this is the error. It's the difference between the measurement or our observation that we can see, and this is the model that we design. So in this case, how do we have different cases to measure this error? And we said we discussed this later, previous lecture. We minimize the sum of the errors, minimize, or we know this is the effect of this case. If we went, for example, take the error equal just the sum of the errors, and we said this is not provide a unique solution, because here we will ignore the errors that comes at the same distance from the best fit line. This is the best fit line. The best fit line, if I assume this is my best fit line and I have some data spread around this one. So for example, this data here, this point and this point, comes at the same distance from this best fit line or regression line. So in this case, the effect of each one will cancel. So this design does not work because the negative and the positive errors can be cancelled and mislead the overall criteria to think there is no error. So we assume there is no error because this resistance or these errors will cancel each other. Another method to measure this error by take the sum of the magnitude of the error. So this also will not work because this will not lead to any unique solution. As we saw here in this graph, if this is, for example, the dash line that we represent this, for example, regression line. Okay, so any point on this line, it will minimize the sum of the absolute value. So in this case, we will not get any unique solution. So what will be better than these three, we will go with the third one. We take the sum of the square of the errors. So computing this type of errors, this will lead to a unique solution. And inshallah, after this method, we will study this least square method. We will study here today. Inshallah, we'll try to cover the correlation coefficients, how good our fitting. After that, we'll study nonlinear polynomials and multivariables. Or instead we have only one variable x, we might have multivariables. We'll study it, and we have plenty of examples, inshallah. And the topic after this one, unit 4, unit 5, we will study the interpolation. This is the same method for plotting, but in that one, in interpolation usually, if we have the line like this one, and we know the relation between x and y, so we need to find the value at discrete point between these two. That means how we protect the value at this point. So for example, if we know our, for example, profit from this year, for example, to 2013. So we went, for example, to protect our profit, for example, and what's the cost and everything, for example, after, for example, 2 years. So if we have certain data, we might protect some values unknowns, and this value usually it's not included in the sheet, so it is easy to find this one. Inshallah, we'll study it after this topic if we have time before the break. So where we stopped last lecture, I think we stopped. Yes, here, let's go to this one. So after that, ya shabab, we write, for example, our equation is a linear way to write the model in the linear equation, as we said, and this is A0 represent the intercept, and A1 represent the slope, and xi is the independent. So one way is here is by minimize this one. That means we'll take the partial derivative with respect to these coefficients. So here, so this is the equation, and this is the error that we have. So what we want, if we want to find the value of the unknowns, we'll try to minimize this equation by taking the partial derivative with respect to A0 and equalize this to 0. And then I will take the partial derivative with respect to A1 and equalize this to 0 as well. And then I will rearrange these two equations. So these two equations that we have it like this one, and this because it is constant, sum of constant. So this is just n a0, and here these terms that's not include a0 or a1 will take it to the left side like this one, and this does not contain a1 and a0 will take it to the left side. Okay, so the rest what we have, I have the terms that contain a0 and a1. After that, by any elimination method, we might find the values of this one. So here a1, this is the form a1, and this is the form of a0, and a0 here we need the value of a1 first, and then we need the mean of of x and also the mean of y's. And this is one example. If we have data, I think this is in the textbook. I hope all of you have the textbook. If you don't have, please inform me, ya shabab. Some quizzes or some example homeworks later will come from directly from the textbook. Usually we refer to the table in the textbook. Okay, no need to cut it. You have because you have the textbook there. If you don't have, shabab, please inform me or share with me on the WhatsApp. So for example, here in this example, we have 7 points of data of x and also 7 points of data of y. So to find a and 0, so we take usually as usual, we have like this one, we have x i's and we have x y I. After that, what we need, I need xi yi, the multiplication, this term. Also, I need x squared. Okay, so here I will multiply x by y, so I will complete this one, and then I will take this square here. Okay, and after that, at the end, here we take the sum of these terms. If we need here, for example, sum of y's, we take sum of y's. The sum of x multiplied by y, this coefficient. The sum of x squares, this column. Okay, and after that also we might compute here we need it the mean of x and also the mean of y. So by using this criteria we find, for example, the value of the slope first, and after that the intercept I0. This also examples, I think we go through this one. This represent the difference when we use the error of estimation SR and the total error ST. Okay, and the total error usually we take the difference between the observation that we have with minus the mean. We squared that. Okay, so here the error SR that's usually we compute, which is the difference between the data that we have and the regression model. Okay, and this the total error, it's the total sum of the squares of the errors between the data points and the mean. Okay, and we'll see the difference. Okay, we'll see the difference. You can see here when we have this is around the mean, if this is the mean value. So here we can see this is around the mean point. Okay, and this also around the regression. Okay, we'll see how when we use a best fit and we, for example, take the difference between the measurement minus, for example, the model or the regression model, this will improve the error. Okay, the error will improve with time. So we can see the error will reduce with time. Okay, because in this graph it is clear for us that the error usually improved with time. What we have today we'll study, inshallah, coloration coefficients and coefficient of determination R, and after that, inshallah, we'll talk about different type, not only linear type of regression. We might have non-linear type and how we linearize these types, the linear types, and also we'll study if we have multiple variables. For example, in the previous example, we have only one variable, it is x. But what about if we have multi variables? So I will study it, inshallah, today. So what about the coloration coefficient? Coloration coefficient or the goodness of the fit will tell us how good we we fit our data. Okay, how could we fit our data? So here usually eitherwise by using a linear function, or for example second first order, or we'll use also coloration coefficient to determine the goodness of our fit when we use, for example, second order equation, or when we use high order polynomial or linear function. All these things we might use by default the ratio of these error. Here, as we know, this is the error, the sum of the errors. As we know, this is we are familiar with this one, and this is the total error. And we said this is the difference between the measurement and the mean. And here, this we call this the coefficient of the determination, R square. R square here determines the percentage, or explains the percentage of data that we use, for example, in our estimation. Here, for example, if the value of R square is equal 1, R square equal 1, that means RS equals 0. If it is 0, so I have ST over ST, so this R square will equal 1. So in this case, this will explain that 100% of the variable of data are used. Here in the second part, if we have, for example, R square is 0. Okay, that means SR is equal S sub T. So in this case, the fit represents no improvement. We don't have any improvement in our fit. R coefficient, this R is the root of R square. We call this the correlation coefficient. Correlation coefficient, we might compute it from this form by taking the square root, or by using this alternative formula. Okay, and both formula, inshallah, will be given during the assignments if you need. Okay, so for a perfect fit, we can see that R square is equal 1. Okay, and SR, S sub R, this equal 0. That means the error between the measurement and the model that we develop is equal 0. Okay, so in this case we get perfect fit. Okay, so if the fit, for example, if R square is equal 0, so that means there is no improvement over the sample criteria of data that we use, okay, by its mean value. So we need, for example, to improve it or to do another criteria to solve it. So, okay, so usually this one, LRS, quantifies the spread of the data about the best fit line, and this R S sub T quantifies the spread of the data about the mean. And this is an example here how we use this, or how we can compute these coefficients. Here we have computing here what we call this the standard deviation. Okay, the standard deviation from the form, we compute here the errors between the y's, and here we have the n minus 1. Okay, n minus 1. So we have n data minus 1. Okay, and here we have the values after that we computed. And here we have the standard error of estimation. We use here sy sub x. Okay, so here we have n minus 2 because we use 2 points of data, A0 and A1. Okay, so, and because here you can see here, because the standard error of estimation is less than the standard deviation, so here the regression model has merit. So to check, for example, the goodness of our estimation, we usually use the coefficient of the determination. Okay, the coefficient of determination, and this coefficient of determination is equal LST. This is ST here, S sub T, minus S sub R over S sub T. Okay, so this is S sub T, this is S sub R. Okay, this is the error. So here we take the difference between them and we find this 0.868. So these results authenticate that 86.8% of the data has been explained by the linear model. That means the linear model, it's ignored around 14% of the data. Okay, so this 86.8% of the data has been explained by this linear model. Okay, Shabab. So here, after that, what we want to study the linear, if we have linear equation, and usually if we have linear equation, because not all the data we can explain it by, for example, linear line. For example, if we have this curve of data, as we know, the linear regression provides a powerful techniques for fitting the best data. Okay. However, it is predict only the fact. Usually, we need to find the relation, or we expect the relation between the data that we have. So usually, Shabab, what we do, usually we plot the data. We plot the data. After that, we look for these graphs, how this data spread on in this window. After that, we can select the best fit method that we can use it to fit all the data, or to fit at least the maximum moment of data. Here, for example, if we have this graph, and this data is represented in terms like polynomial. It's not, for example, a relation between the input and output is linear. So in this case, we can find that the linear, it might not give us the best fit here. Okay, because here, if we have a linear function here, or a linear relation, will not, for example, will not explain the data in a good way. So in this case, we need to have, or to use some linear, for example, or more high order, for example, polynomial to represent this data, instead of we use only the linear relation. So usually, Shabab, if we have the linear relation between the input and output, in some ways, you might have, for example, you build a table. You have, for example, this x and this is y, and you put, for example, you fill the table in terms of linear. But here, to simplify this method, we do some techniques by linearize the linear relation between the input and the output. That means we convert then the equation, or the relation from linear way to a linear ways. So this is, for example, some examples of the nonlinear relation between input and output. Look here, if we have here exponential as a relation between the input and output, and y equal alpha 1 exponential power beta 1 x, and the relation here between the data that we have, x and y, is exponential relation. So one way to do this one, to linearize this equation, we just apply anti-exponential. So, and we know an anti-exponential is usually the ln logarithm like this one. If we apply ln logarithm on both sides, if we apply ln here at both sides, so here I will get ln y, okay, and ln y, and here I have ln alpha plus beta x ln e, okay, beta x ln e, and we know the value of ln e. Okay, so after that, this is equal 1. So as a result, we have here a linear relation between these two. So here, for example, this now the new equation after I apply ln. So might I assume here a new variable z that's equal ln e, or ln y, sorry. Okay, might I use here a new variable that's represent, for example, or assume here a new variable, new observation So this observation is equal nu, for example, ln y. So as a result of this one, what we do, so I just also here I have the value of alpha. This term I might also represent it by ordinated, or I use a new variable to have it in another way. Also, for example, a1 bar. Today, this is a1 bar. I might type it, for example, this bar might equal ln a1. So as a result of this one, so I can have a linear relation now. I can type z will equal a1 bar plus beta 1x. So now I have a linear relation. Now I have a linear relation between the inputs and the outputs. I have here the inputs that we have x's for the independent variables, that x is here. I have a linear relation between it and the output that I have. So I can build my table like that. So this is the x's that I have, and this is the y. Okay, so here is z. I can type one column here. Z is equal ln x, ln y, sorry. So I find value of z because I need the value of z. And here I have x and z. Okay, so what's unknown with me is this coefficient, a1 bar and beta. I filled this one. So after I will use the same criteria that we used before for a0 and a1. I will use the same form. After that, so I need to multiply or to find zx, okay, and I have to find the sum of x square, okay, also the sum of x and the sum of zeta. After I solve this one, I will find the value of alpha 1 bar and also beta 1 bar. If I find the value of alpha 1 bar and beta 1 bar, so then I will return the solution to the normal case or to the original function by apply anti-algorithm. So in this case, I can find the value of alpha from alpha bar, and also I find the value of y. Y is known because we are interested in this parameter only. So if I find here the alpha and beta, so this is what we need. So beta I can get it directly, and alpha bar I can get it. Alpha I can get it from the anti ln for alpha. So in this case we can solve this problem. So that means here, ya shabab, if we have any nonlinear equation, we try to linearize this one. Sometimes we need our skills that we studied before, and usually we have three types of questions we call these nonlinears in this course. We have use exponential of power exponential, or for example nonlinear order. If we have nonlinear here of power equation, if we have x of power something, or if we have saturation ratio or fraction ratio. Okay, so in this case, one of them, you should be familiar with all of this method and how we use this one to these, for example, anti-methods to linearize these methods. Okay, or sometimes we have sine, cosine, but this cosine is usually it is difficult to linearize it. Only if we convert it, for example, to Euler method. After that, we apply a ln, and then, for example, we continue with this one. Any question here, ya shabab? Okay, so we can do linearization for this one. Here, for example, for if we have a power system, we can apply here also logo for this side, for both side here. We'll do the same criteria for this one, and we'll get it this in this form. Okay, and after that, we might define, if we want to define, for example, new variables here, this, for example, to be z, and beta here I have it, and X here, for example, you can logo or log X or logarithm X, I can define it, for example, any variable, capital X or X bar, for example, like this one. Okay, and this multiplied by beta 2. And this coefficient, as we said, you might define it, for example, A2. After that, we build the table for linear regression, and we use the formula for linear regression. And we know here we have new variables. So el beta here represents el A1 in the form of linear regression. El alpha 2 is intercept A0. After that, we find these two parameters from the table or from the formula that we have, and then we solve the problem. That means we transfer the linear relation to, or we convert the linear relation to a linear relation. Okay. And after that, we transfer the relation back, for example, to define the exponential relation. Okay, and then after we do this one, we back, for example, transfer the parameter back, we return back, we used anti-inverse, anti of the logo here, for example, to get the relation of the exponential function. Here, for example, for if we have saturation, if I have y here, usually we assume I have new variable z, it's equal 1 over y. Okay, assume like this one. So as this result, I might have a new, I will linearize this one. So here also, this one over x, I can assume a new variable, x bar, for example. And this plus this term, I can assume it a0, 1 over a3 or alpha 3. And this term beta over a3, also I can assume it, for example, a1. Okay, and then I have here z. So now I have linear relation. I have here this value is a1, this a1 and this a0, and I know this one. I will build my table. I have column, for example, now extra column. I have x and y. I have one column 1 over x. This will be this variable x bar. I have another column for 1 over y, so this will be z. And after that, we need to fill to solve this problem for this parameter, for the new parameter. So I need to find x bar, sum of x bar multiplied by z, and also sum of x square, and the square of the sum of x bar. And after that, we find the value of alpha 1, alpha 0, and alpha 1. From this value, I will compute alpha 0 or alpha 3 here. Alpha 0, so I will compute 1 over alpha 0. This will be alpha 3. After that, I can compute the value of beta. Okay, beta 3. If we compute these two parameters, alpha 3 and beta 3, we can find the relation or linear relation now between our independent x and the y's. Any questions, Shabab? So usually this linear relation, it comes from the presence of the noise in our system. So, okay, so this noise usually affect the presentation of that.
دكتور
Yes, تفضل.
ليه قلبت كل المعادلة؟ يعني خليتها z equal 1 over y.
Which one?
آخر معادلة أنت خليت z equal 1 over y.
Yeah, here we assume. We assume here because we want to inverse this one. Okay, so here I have y and this equal this fraction for ratio equation. Okay, so what I want to do, because I want to flip this equation. So here what I have, so I'll assume I will do this one first. 1 over y, this will equal, okay, I will swap this. I have here beta alpha 3 multiplied by beta plus x over x. So I will get this equation. This is the equation. After we take the inverse 1 over y. Okay, هتلاقي عندك هذا equation. To represent this in linear way, it might be confused for you. Okay, to represent in linear way, because in our model linear way we have y it's equal alpha or a0 plus a1 multiplied by x, a1 multiplied by x. So as a result here, we try to simplify our solution here, okay, or to represent the equation in a linear way. So to represent the equation linear way, I will assume 1 over y equals z, new variable. Okay, so this will not affect my solution because in my columns or the Excel sheet that you have here x and you have y, and here you represent z, and you know z equal 1 over y. Okay, so now I will solve the problem in terms of the new variable. I will find now 1 over y. And here also, the second term, this coefficient, you might use it like this one, but it's easy to define it a new variable. Okay, this is unknown. Okay, so I define it, for example, alpha 1 or a1. The coefficient here that I have it, and also the x, let's x, so here I define it, for example, x bar. Okay, so after that, I will solve my problem in terms of z and x bar, not in terms of x and y. I will solve the problem using this formula here that we have it. Let's write the formula. Yeah, here, instead of x, I will have x bar. Here, instead of y, I will have z. Okay, so I will complete this one to find alpha 1 and then alpha 0. From alpha 0, I can find 1 over alpha 3. After that, I can find beta 3 from that. And then if I compute these coefficients, that means I solve this one. I will return the problem back to this one. Clear the point?
Yes, clear.
Yeah, we just linearize. We want to represent the equation in a linear form. So for example, here you have ln. This logo, for example, here I have y and this is exponential. So what we want to do, we want to apply anti-exponential. What's the anti-exponential? Is ln. Okay, so apply ln here for both side or on both side. So in this case, I represent this in linear function. Here, this is ln of e is equal 1. So I have here ln y equal ln alpha 1 plus beta x. This one, this coefficient, to have it in this form, you can see I have here, this is the intercept. Ln alpha is the intercept. So easy, I can define it, for example, a0, to have it in this form. Also, ln y, here I represent it by z, to have new equation, okay? And here I have beta x, so it is okay. I don't have to transfer this one. So now I have z equal ln y, alpha 0 or alpha 1, it's equal ln alpha. After that, I will do my analyze to find the value of the coefficient beta 1 and alpha 1 dash. And then, for example, I will transfer again to the original values. I will apply here, for example, anti-y, for example. No need for anti-y. I need here anti for this parameter, for alpha 1 bar, okay, to find alpha. After that, I will substitute in the solution here that we have. Any question here, ya shabab? Okay. This is an example, what we have here in from the textbook. You can see this example 17.4. Okay, it's given here this polynomial and the question how to find the curve fit of this polynomial. Okay, so one way, because here we have power function, we apply logo base 10, on both sides. I have here log y, and here I have, because this is here I have logo or log here alpha sub 2, this coefficient, plus alpha 2 or beta 2 log x. Okay, this will be the second coefficient. Here يا شباب we build our table based on that. I have x, I have y's. This will be log of x, and this will be the log of y's. Okay, so after that, what we need to apply the best fit formula. Okay, how we can find the value of alpha. This alpha, you can assume it is 0. Okay, and here I can assume log of x is z, for example, or x bar, or x1. Okay, and this coefficient L beta is the same beta. Okay, and beta here is a1. Just apply the formula that we have. You will find, for example, two equation, and from this equation, after we minimize this with respect to this coefficient, alpha 2 and also log alpha 2 here, we minimize the equation. That means we take a derivative with respect to this one, and after that we equalize this to 0. You will have a matrix 2 by 2, and from this matrix we find the values of x, of alpha, logo alpha 2 or alpha 0, and then we apply the inverse of this one. The formula that we use, this one, the form that we have. This is the form. This is the form that we have. So just use here. This is to compute the slope. So this is to compute the slope, any value. So this is the slope, and here this is the intercept. And here, shabab, don't forget, if you transfer x will not still the same x, or y is not still the same y. We have to double check this one. Okay, students usually they use the same formula, and they multiply after linearize. They apply, for example, sum of x multiplied by sum of y, while the linear equation there is different if we linearize. Okay. So if we linearize this one, we find the values of alpha 2 is equal 0.5, and here beta 2 is equal 1.75. Okay, so we can find this equation. We solve this. So that means we linearize the equation. This is the function, the linear relation between the input and output, and this is the approximation or linearized equation for this one, for the equation. So this is another example. Determine the fit exponential equation. This is the equation using least square method. So given the data here, I have here 4 points, 4 data points, and x 2, 3, 4, 5, and this is the value of y's. So the same things, we fit the data like this one. After that, we take the logarithm on both sides. We'll get this equation. Okay. So after that, to simplify, I will assume this is equal y capital. Okay, and this coefficient here, I will assume it a. Okay, and this here, log x, I will assume it, for example, x capital. So I have this equation now, linear relation. So here, this is the intercept, a0, and this is the value of the slope. After that, I have this is the formula that we have. Normal equation, for example, for a linear least square or a linear regression. This is the form. This is the sum of the y's, y capital, not y's. Okay, this is y capital, while y capital, it's log of y. And here, this is alpha or n multiplied by a. Okay, and I will get the value of a. After that, I will apply inverse or anti-logo. Here, b multiplied by the sum of x capital. Okay, this is x capital, not x, the small x. So x capital, we need to add more columns. And here, the sum of x multiplied by y, a multiplied by sum of x, and this also, this should be squared. Okay, this should be x squared. So this is the table represent this one that we have. So this is the x's, and this is the y's, and this is the x capital that I create, and this is the y capital. Okay, so here we take square for printing. It's represent. This is x capital square. Okay, and this is x capital multiplied by y capital. After that, we apply the form. We'll get these two equations in terms of a capital and b capital, and b, a capital and b, and this is coefficient. And then we solve the equation. I will get a capital, for example, equal 0.868, and also here beta or b equal this value. So we know now we need to find the value of the coefficient that we have it here. This coefficient, b, I have the value of b already. I need the value of a, and the value of a is just anti-logo of a capital. Okay, so I find the value of a. So our goal here to find the value of the coefficient b and a. So b we get it directly from the equation, but a small, I need to apply. I have here a capital, so I need to apply anti-logo. Look here. So here we apply anti-logarithm here. So to find this one, I will get the value of a small. So after that, we just substitute in our equation. So this will be the model equation, or the best fit equation for this one. Any question? The steps are inshallah to be clear for you, but usually we try to practice this one, not related to the exam, because sometimes we made mistakes in the calculations. This will affect the results. Okay, so please shabab, try to practice more the examples and try to solve more problems from the old exams, from the old homeworks, the quizzes. That will help you inshallah. Any question, ya shabab, until here? We can go to the next one. Okay, so in this section, we will study polynomial regression. That means when we fit the data in forms of second order or more. Okay, so otherwise, for example, second order, we call this quadratic regression, or for example, high order from the 3 to above or higher. So what we do usually, what we have before, we have our observation y, and we have here this the linear coefficient. So if we need, for example, to have second order polynomial, we need to have the second order coefficient a2 multiplied by x power 2. Okay, and this should be plus the error, because here we have noisy data. So the sum of the errors SR or S sub R here, as we know, this is equal our measurement minus the model, or subtract the model. The model that we have is A0 minus A1xi minus A2 xi squared. Okay, so here we have the same x, but we have two variables. So now to find what's our interest here is to find the value of the coefficients A0 and A1 and A3, sorry, A0, A1 and A2, that's partial derivative with respect to this coefficient for this error, for the error. Okay, so that means we'll take partial derivative of the error with respect to A0, and we equalize this to 0. And then we'll take partial derivative of the RS, sorry, sub R, for example, here with respect to A1, and we equalize this to 0. The same thing is what we did before, and this then, for example, for A2, and we equalize this to 0. As a result, after rearranging these equations, we'll get these two or these three equations. These three equation, we have three equation and three parameters. So we have 3 by 3 equation. Okay, so the solution of this one, we might use the Gaussian method to solve this one. Gaussian elimination method to find the value of the coefficient A0, A1, and A2. Okay, so here errors or standard errors for estimation, we can represent it in this form. Here is y sub x, it's equal here the errors of the, or the sum of the errors, or the sum squares of the errors over n minus m plus 1. M here represent the order, the highest order that we use. Okay, here for example, in our case here, for example, in this example, we use second order. So in this case, I have n minus 2 plus 1, so n minus 3. So if you use the third order, so here you have n minus 3 plus 1. Okay, so in our example here, the order is 2, so this will be n minus 2 plus 1, that means n minus 3. Any question? So it's the same thing as what we do, just we differentiate the error S sub r with respect to each coefficient, and we set these to 0. Okay, so this is the standard error of estimation. And يا شباب, the textbook is very important in this topic, because to have more information about these examples and explanation about how we use this one, you will find it from the textbook. Okay. So here, يا شباب, you can see, as we said, here we have m is the order plus 1. This is an example, يا شباب, for quadratic form. And the same example what we used before, what we have before, the same example what we did here. Let's see how we get. So this is the result here. What we have 86.8% of the data it's used when we use linear estimation. Memorize this one. And if we use here the same model, the same data, but here we have it in, we fit it using quadratic form, or quadratic regression. So by using this quadratic regression, and we find here the errors between the data that we have and the mean, and here the square root of the error. So we will get, for example, after that we find this coefficient that we needed to fill the matrix. We will have this matrix 3 by 3 by using any method. You will find this coefficient A0, A1, and A2. Usually we use Gaussian elimination, Gaussian Naive elimination, or any method you used it before that you use it here to find the solution here. So if we get these equations, and after that we try to estimate the coefficient of determination, r square, we'll find r square is equal 0.99851. That means the result indicates that 99.85% of the original constraint has been explained by this model. This result supports that, or concludes that the quadratic equation represent an excellent fit if we compare this with linear. So usually the quadratic, if you go with quadratic, is more difficult, but represent, or we can say it's represent the data in a good way. So usually the form, يا شباب, no need to derive this form in the exam. So usually this will be given for quadratic, and also for a linear regression, for the quadratic regression. Also for linearization, the form usually. Okay, so just what we want from you to build your table, to fill it correctly. After that, you compute this coefficient correctly. Please to practice this. Try to practice this formula, and to find the coefficient. And after that, sometimes we stop here, or sometimes we need to find, for example, the errors, or sometimes we need to find the coefficients depending on the question. So here, if you want to do this one, so you need to do also elimination, Gaussian elimination here. Any question? Okay, so the third section, if you don't have any question, we will go further. Okay, so the third section, when we have a multiple linear regression, this usually we have so far fit lines or curves to a data described by a single variables. So what we described before, what we have a single variable is x. Okay, so we have one variable x. And here, when we talk about multiple linear regression, we have here different variables or multiple variables. Okay, so sometimes we have the function, it's represented by multiple variables. Or sometimes, as we said, we have the function single variables like what we have here, but with different order. Okay, polynomial. And instead we have a linear, we have single variable, but we have a polynomial regression. So here we have in the multiple variables, we have here x0 plus a1, x1 plus a2, x2, for example, plus the error. As we said in the regression, we have the noise. So you have to include the noisy data. So after that, this will be the error that we have, or the error, or the sum of the error square, or squared error. And after that, we subtract the model from the data that we have. And then we minimize. If we went here to find the best fit, we need to find the value of these coefficients, A0, A1, and A2. That means we need to differentiate S sub R with respect to the coefficients that we have. I have coefficient A0, A1, and A2. And after that, I will equalize these to 0. Because here I have uh, three equations, because here we build three equations with respect to three parameters or three coefficients. So as a result, I will get a matrix 3 by 3. So the normal equation here, we can solve it in this matrix by solving any method of elimination. Any method of elimination, we might eliminate this one to find the solution of this equation. Okay, so this is an example also from the textbook. Here we have a data or equation for linear regression for multiple variables. Here we have x1 and we have x2, and this is our observation. So we build our model like this one. So I have here two x's, so here this will be plus e, like this. So what's objective here is to fill this table. You can see this is the table here. I have y and I have x and I have x2, because here the form that I need. You can see here I have xi, sum of x1s, sum of x1 here, and here the sum of x2. So I have also sum of x multiplied by x2. Okay, so all these things I need to compute. And here also I have here x2 squared, and here sum of y, sum of x1 multiplied by y, sum of x2 multiplied by y. So these columns I want to fill. I have y's, I have x's, and I have x2, x1, and x2. So here I squared the value of x, 0 squared, so this will be 0. 2 square will be 4. Here 2.5 squared, this will be 6.25, like this one. I fill this one. After that, I will square the column of x2 here, for example, and then I multiply x1 by x2 and x1 by y and x2 by y. After that, we fill this form, and this form usually will be given. So as a result of this one, you will get this model equation, okay, or this model or system of equation. So what we want here, just we solve this equation correctly by using any method of techniques. I think your calculator will help you to do this one, yes? By calculator, directly you can compute this one, 3 by 3. Yes, I would say yes, okay. Okay. Okay, Shabab, so after that, we can solve this equation and we find
how can we do it by calculate the matrix if you know it?
Who's this us? For me, I never used calculators from baccalaureate. Okay, so it is years we used the old one before. So this years, for the last 15 years, I don't use calculator, only a little bit in the small exams that need calculators. But in usually in high education, usually we use softwares in our system engineering department. So I don't know. I think the student, they can do this one. They insert this 3 by 3. I think they solve it maximum will be 3 by 3 by calculator, if I'm not sure or not. Some examples you can expect that sometimes we ask you to use a buffed here. If you get this equation, use buffed. For example, we have one question that's contain two problems, or I can ask you to use, for example, NIF elimination, not using the calculator. You have to show you all the results. Okay. And also sometimes I need the coefficients, I need the models, so you have freedom here to use the calculator directly. After that, I think you can use, but I'm not sure. في أحد من الشباب they can answer this question.
I tried, but I didn't find it in the calculator.
Okay, then no. Okay, شباب. So this is the topics that we want to cover in this unit. Here we studied linear regression. Regarding the calculator, شباب, anyone know how he used this one? He can share the information with us, please. Okay. To help his classmates here. So what we studied here, we studied the linear regression or the least square linear regression. And after that, we study how we can compute the goodness of our fitting by computing the standard deviation or the deviation of the error. And also we compute the error by itself. And then, for example, how we design the model for linear system. And also we study if we have nonlinear equation or nonlinear relation between the input and the output, and we say sometimes we need to plot the data after that to look for the relation between the input and the output. Like if you went, for example, to find the roots of the equation. Okay, in graphical presentation or graphical model, we plot the data. After that, we look for the graph. After that, we can estimate the upper bound and the lower bound. We start from this one, and we reduce the interval by using bisection until we get the exact solution of the roots. Here we need in the nonlinear usually for example, any functions, we need to plot the data. After that, we look for the data to see or to inspect what will be the best way to fit this data. Otherwise, linear, nonlinear, quadratic, or we have, for example, multi-variables data. So after that, we study how we linearize these nonlinear equations. And in section 2 in the textbook, we'll see how we study nonlinear polynomial, if we have nonlinear, and we focus here on the quadratic type. And the form, as I told you, this will be given. No need to memorize this one. So this one, if you need it, and this one, and this will be given. Okay. After that, we study also multi variables, and instead we have only one coefficient x or independent x. We have multiple or two or more independent variables. So x1, x2, x3. Okay. So in this case, again, we will take the partial derivative with respect to this coefficient that we have, a0, a1, and a2. And then, for example, we minimize this and equalize this to 0. We'll get this equation. So please, ya shabab, during the exam, make the tables clear. So for any column, you have credit. يعني don't write here, for example, you give me the final answer. I don't want the final answer directly. Usually in the exam, you'll write the solution in details. So these columns, for example, you have some grades, for example, 1 point and this 1 point, this 1 point. If you miss one of them, you will miss grades. So you cannot, because if you need this one in the solution, you have to write it. But if you, for example, jump from this equation and try to give me these columns and give me the final answer or the final results, you'll not get the final or the full grades. You have to usually all the question I will type at the top of the exam. Enter your name, write all the solution in details or detailed solutions.
Maybe we can use like Excel, make easy.
No, exam is written. You cannot use
not for the exam.
Excel.
I mean the quizzes.
Yeah, quizzes.
Or
No,
maybe the exam is online, no problem. But I mean for the quizzes.
no quiz.
Excel
No, quizzes you cannot use Excel. You have to. Okay, we expect you don't use anything because we monitor this one. We no need to use the softwares.
Okay. But I think maybe you can use Excel or MATLAB homework or something like this.
If you use the MATLAB, so no way يعني, to do this one. To study the steps here, because if you have, for example, the tools for this algorithm, just you will enter the y's and you will enter the x, they will give you the solution, yes? Okay, without all this calculation, you will not do this calculation. The software will do this calculation and will give you the results only. Okay, so in this case, what's the benefit? So the quiz should be 2 minutes like this one.
We need to make the calculation.
Yeah. What is allowed? Only the calculator. Calculator here only allowed in the quizzes and this one. Also the homeworks. If I give you this one, you have to write all the things in details. If you give me the final answer, I will not accept this one. Okay, so I have credit for the final answer. For example, I put 1 point here for the final answer. So if you solve, you give me only the final answer, you will get 1 point from the total. So usually I distributed the grades for these steps. This 1 point, 1 point, 1 point, 1 point, like this one. So I have here, for example, 6 points. Final answer only 1 point. The model here only 1 point, for example, and this, for example, 1 point. The matrix here 1 point. If you give me this one, you will get 1 point only. Without details, you will get 1 point. To be clear with you.
Makes sense.
Yes. Okay. So please, ya shabab, don't try to use softwares and the homeworks and the quizzes, because that's what I saw in the first quiz. Student, they gave me the solution, I don't know how they get it. Steps is not clear. They even the derivative is wrong, but the final solution is correct. Okay, so they cannot derive, for example, or compute the derivative over the exponential, but the final result, they get the correct solution. I don't know how they get it. So I have the correct solution at the answer, and all the steps at the beginning are wrong. And how they calculate, I don't know. So in this case, I will inform you, Shabab. If you get it, anyway, I will not focus on the final answer. The final answer is just 1 point. Okay, so all the steps you should show during the solution. Okay, so here, ya shabab, let's summarize this what we have here in the slides. So we'll have 2 examples here. You will see, inshallah, you can solve it or go through them and at home. Here, what we study, the method that we study, the linear regression, and this is the model of the linear, and this is the form that we use it to compute this coefficient. Here also we have polynomial. If we have only one variable, but with high order, okay. And this also will be the error, and this is the coloration determinant or coefficient of determination. And here we have multiple linear regression. We have multiple variables, not only one variable, we have multiple variables. And that's what we study here. Here we have another example from one of the exams before. Here, for example, given this data, use a linear regression to fit the straight line of this data and calculate the coefficient of determination. So this data is given. So what we need to use the form that we have. Okay, this form, the sum of this one. So let's cut this one. I will put it here. just to. Okay, I have x's and I have y. So here I have n is equal 5 points. Okay, so here n multiplied by y. So you build our columns. You should build the columns, or you calculate it like this one. So usually I will give you the table. Usually we give you the table to fill it. Okay, and sometimes to have yani correct way, or you build it like this one. You can compute, for example, x's and y's and this one. Okay, if the table is given, you have to fill the table. If not given, you can compute, for example, sum of x's, sum of y's, sum of this one. If this table is not correct, this will affect. So if you have, for example, this using the calculator, user student prefer to take a sum of this easy by using the calculator. So after that, you'll use this form to find alpha and beta, and then, for example, the model. And from this model, you might compute, for example, R square. Okay, from this form that is given, because we have two form of the R. Okay, so otherwise you compute S of t minus S of R over S of t. Okay, if you don't have S of t, so just use this form, because all the information that we need is here. Okay, so this is 5 is the number of the data multiplied by the sum of x multiplied by y. Okay, and so here we have also here sum of x multiplied by 3.8, and this should be a sum of y's. Okay, and over this coefficient, this square. After that, you will take the value here. This is another question, but this is a little bit new here. Linearize the model, and here the model you can see exponential, but here we have, you can see this clear, يا شباب, or I zoom? I should zoom this one.
Zoom a little bit.
Now clear? Better?
Yes.
Yes.
Okay, you can see this equation here. This is y equal axe beta multiplied by x, power beta multiplied by x. So this is the model that we need. So because this we have exponential here. So just we take ln for both sides. Okay, so here they have one step here to linearize this one. They divided over x. Okay, divided over x. Here we have different method to do this solution. So here they divided over x both sides. So here understood the new variable here that I have it, z, for example, it's equal y over x. Okay, y over x. Any step you can do it to get a linear equation, but should be correct. So if I divide it over x, I will get here y over x. So here ln y over x. And here I have ln alpha plus beta x. So now this variable now, I might define it as z, for example. Okay, this z. And after that, we have a linear relation, and this ln alpha is alpha 0, for example, in our equation, plus beta x. So after that, we build our table based on this one. I have zeta. Zeta is ln y over x. So that means I have to take y over x one column, and then, for example, ln will be zeta will be the ln of this column. Okay, so you will have here, this is the x, and this is y column. Here I have y over x column. Okay, and then, for example, to find z will be ln x, or ln this term, y over x. Okay, and this equal this one, so this is z, and x is the same. And now I will build this table. I will use these two columns now. This is my start now. Okay, sorry, not this one. I will use this z, or we call this z zeta, and x is here, to find the value of alpha and beta. Okay, so here I have x capital. You can see this is defined as y capital, and this is the same x. We build this the table now. We create a new table. After that, we find these terms that we need. We'll use the formula of least square to find the value of alpha and alpha 0. And then, for example, I get alpha here. Okay, and alpha, it is equal the inverse of this one, this coefficient here. Because here you can see alpha 0 is nothing, just anti-len of alpha. Okay, so here we compute this one, we apply exponential here to find alpha, and after that we substitute in the model that we have. This is the model that we have. For finding, for example, the goodness of our model, we just use this one. And this linear model, you can see, explains 99.94% of the uncertainty that we have, or of the data that we have. Okay, inshallah you have plenty of this one. If you have any problems from all the exams, all the homeworks,